Okay, so let us start today's lecture, and we will be continuing with probability theory. So we will review various examples, talk about expectations, and then eventually talk about Benford's law. So let us begin by reviewing independence. So in the last class, in the last lecture, we discussed about independence of two events, which is expressed by the mathematical expression in the following, which is expressed as a mathematical equation in the following sense. So of course there is an intuitive notion of independence of events, but mathematically it is expressed by an equation which is of the following form. So two events A and B are independent if and only if the probability of A intersection B, where A intersection B is the intersection of A and B when you think of them as sets. So this is the in other words, in words, it is the event that both A and B occur. The probability of that is equal to the probability of A times the probability of B. Okay. So let us take an example. There are 12 cars in a race. Acura and Benz are two of those cars. Each car has an equal chance of winning. Let A and B be the event that Acura and Benz win the race respectively. So are the events independent? So again we have to check if A is the event that Acura wins and B is the event that Benz wins. So then you have to check these equalities, check this equation, check if this equation is true in order to verify whether the two events are independent or not. So let us go about doing that. So there are 12 cars in a race, each car has an equal chance of winning. So the probability of Acura winning is 1 over 12. The probability of Benz winning, which is denoted by B, is also 1 over 12. So probability of A times probability of B is 1 over 12 times 1 over 12. And probability of A intersection B is, if you think of A intersection B, it means that both Acura and Benz win the race, but in the same race there cannot be two winners. So the probability of both Acura and Benz winning the race is 0. In other words, the probability of A intersection B is 0. And since 0 is not the same as 1 over 12 times 1 over 12, the two events are not independent and they are called dependent. Okay. So this fits our common sense because there can surely be only one winner and the events are related. Any questions? So let us continue further. So let us think of false positives. So a false positive error, or in short a false positive, is commonly called a false alarm. So it is a result that indicates a given condition exists when it does not. So think of in terms of medical diagnosis. So suppose the medical diagnosis report tells that you are having a certain medical condition, certain disease, when it is actually not the case. So this is what is described as false positive. So for example, in the case of the boy who cried wolf, the condition tested for was, is there a wolf near the herd, right? So you have all heard of the story that there was this boy who used to take his herd to graze every day, and every day used to cry wolf, wolf, and then everyone would come and then there would be no wolf, so they would scold the boy. And eventually one day when he took the herd to graze and a real wolf came, he again cried wolf, wolf, but that day no one came because they thought that he was bluffing, right? So you all remember this story. So if you look at the first few days, he was crying wolf when there was actually no wolf, right? So this is an example of a false positive. A false negative, on the other hand, is a situation when there some condition is actually existing, but the report says that there is no problem, there is no issue, there is no medical condition existing. So here, so an example is that a truly guilty prisoner is acquitted of a crime. So the condition that we were looking for actually exists, but the report or our procedure somehow throws up the answer that it does not. Okay. So here is an example. Miss Wong says that she is itchy. Now there is a test for allergy to cats, but this test is not always right. So this often happens. So you have some medical test, and it is and such tests are often right with high chance, with a high probability, but with some small chance there is a possibility of an error. So for people, so for example, in the case of allergy to cats, for people who really do have the allergy, the test says yes 80% of the time. So so if you have the allergy, the test says the test will detect the allergy 80% of the time. For people who do not have the allergy, the test says yes 10% of the time. So this is the false positive. You do not have the allergy, but the test says yes. So you are looking for a condition. The condition is not actually occurring as a ground truth, but the test falsely reports that the condition is actually there in the ground. Okay. So that percent is 10%, and this is the chance of a false positive. If 1% of the population, the question is that if 1% of the population has the allergy and Miss Wong's test says yes, what are the chances that she really has the allergy? So basically what you have to rule out is a false positive, right? So since the test is saying yes, there can be two eventualities. So it might be the case that Miss Wong actually has the allergy, and the test is detecting that allergy and therefore saying yes, which is the good case. And the other case is the bad case, which is what we want to rule out, which is the case that Miss Wong actually doesn't have the allergy, but the test is reporting it wrongly as the existence of an allergy. So it's in other words, it's a false positive. Okay. So let's do that. So this is really an exercise on conditional probability, which is another item which we have discussed. So let A be the event of having an allergy and B be the test saying yes. What we want to find that given the test says yes, what is the chance of actually having an allergy? So let's work it out. So what is the probability of having an allergy? Well, 1% of the population has the allergy. So the probability of having an allergy is 1% converted to a fraction. So 1% is just 1 over 100, which is 0.01, right? So 1% corresponds to 1 over 100, which is 0.01. What is the so B is the test saying yes. So what is the probability of B? We will calculate the probability of B in a moment, but it turns out then that in this example, calculating the probability of A intersection B is easier. So let's do that first. So probability of A intersection B is that the person has the allergy and the test detects and the test detects the allergy and says yes. So this is equal to and whether the person has the allergy or not and whether the test is saying yes or not is independent. So you can write this as probability A, or rather the way you can write this is that probability A intersection B, without considering whether A and B are independent, you can think of probability A intersection B as probability of B given A times probability of A, right? So now let us look at the given data. So this is basically coming from the equation that probability of B given A is probability of B A intersection B divided by probability of A, right. So, if you take this equation and take probability of A to the other side, you get this. Okay. So, we will calculate the probability of A intersection B using this equation. So, what is the probability of A intersection B? It is the probability of B given A times probability of A. So, let us now look for these quantities in the given data. So, probability of A is already given to be 0.01. So, this is good. What is the probability of B given A? Well, for people who really has the allergy, so given that you have the allergy, the test detects it 80% of the time. So, given that you have the allergy, the test says yes with probability 80%, which is in terms of fractions, it is in terms of fractions, it is 80 over 100, which is 0.08. Okay. So, this is 0.08 and this is 0.01. So, 80 over 100 is 0.8, excuse me. So, this is probability of B given A is 0.8 and probability of A is 0.01. So, if you multiply them, it is just 0.008. Okay. So, we have so far probability of A, probability of A intersection B. Now, we need to find probability of B, because if we are going to find probability of A intersection B, then by definition this is probability of A. If you are to find probability of A given B, this is the probability of A intersection B divided by probability of B. Okay. So, what is this probability? So, let us, so this we have already calculated, we want to find probability of B. So, what is probability of B? Probability of B is, you can decompose it as B is, so you can decompose this probability in terms of whether A occurs or whether A does not occur. So, if you think of B here, then A is somewhere here, if you think of them as these circles. So, this is the intersection A intersection B. So, B is either the shaded region, which is A intersection B, or the rest of it, which is just the part of B that lies outside of A. So, this is exactly A complement intersection B. Okay. So, and these are disjoint areas, as you can see, the shaded region and the unshaded part here. So, the probability of B is nothing but the probability, the area of the shaded region, which is probability of A intersection B, plus the area of this unshaded part of B, which is A complement intersected with B. So, probability of B is the probability of A intersection B plus probability of A complement intersection B. So, A intersection B we have already calculated as 0.008. So, let us now calculate probability A complement intersection B. What is the probability of A complement intersection B? Well, so, probability of A complement intersection B is nothing but probability of B given A complement times probability of A complement, right, in the same, using the same idea as here. So, what is the probability of A complement? 1% of the population has the allergy, so 99% of the population does not have the allergy, and A is the event of having the allergy, so A complement is the event of not having the allergy. So, 99% of the population does not have the allergy, so in terms of fractions that is 0.99, so probability of A complement is 0.99. What is the probability of B given A complement? So, let us decipher the event B given A complement. So, B given A complement is the following event. So, B is the test saying yes and A complement is the person not having the allergy. So, probability of B given A complement is the probability of the test saying yes given that you do not have the allergy, right. In other words, of the probability of false positive. So, for people who do not have the allergy, the test says yes 10% of the time. So, this is exactly probability of B given a complement. So, this is exactly 10% or in terms of fraction 0.1. Okay? And so, probability of A complement intersection B is 0.1 times 0.99, and if you sum them it is 0.107. So, now we have calculated probability of A intersection B, we have calculated probability of B. So, we calculate probability of A given B by writing it as probability of A intersection B divided by the probability of B, plug in the values that we have calculated before for the numerator and the denominator, and get the final answer as approximately 7%. Okay? So, given the test has says yes, the chances that Miss Wong really has the allergy is 7%. It's that low. Okay, any questions? So, let us go on to the next example. So, a cab was involved in a hit and run accident at night. There are only 2 cab companies in the city, green and blue. Each cab is equally likely to have an accident, and the following facts are known. 85% of the cabs are green and 50% of the cabs are blue. A witness has identified the cab as blue. The court tested that the reliability of the witness under the conditions and the reliability of the witness is of the following form. The witness correctly identified each of the 2 colors 80% of the time and failed 20% of the time. So, the question is that what is the chance that the cab in the accident is actually blue? So, there are cabs of 2 colors, green and blue, and one of them was identified in a hit and run accident. So, no one knows what was the exact color of the car. There is only one witness. This witness identified the fleeing cab, absconding cab as blue. However, there is a catch, and the catch is that the witness is not always correct in identifying the color. So, there are some probabilities involved there, and he identifies each of the 2 colors correctly 80% with 80% chance, and fails and incorrectly identifies the color of the cab with 20% chance. So, given that the witness has identified the cab as blue, what is the chance that the cab in the accident is actually blue? Okay? So, this chance we want to estimate. So, again as usual, let A be the event that blue cab was actually involved in the accident, and B be the event that the witness identifies the cab as blue. So, we want to find the probability A intersection B, A given B. So, the probability of the cab being actually blue given that the witness has identified it as being blue. Okay. So, let us take an example. So, let us calculate the various probabilities. So, again we will what do we need? We need probability A intersection B and probability B. So, what is the probability of so let us calculate the various probabilities, what the data that is given to us. We know that 15% of the cabs are blue. So, and since A is the event that the cab was blue, the chance of a random cab being blue is 15%, right? So, the probability of A complement is just 100 minus 15%, or 1 minus 0.15, which is 0.85. So, what is this we have. So, let us now interpret the other data in terms of conditional probabilities. So, we know that if the cab was actually blue, then the witness will identify it as blue with probability 80%, right? Because the color is identified correctly with identified correctly by the witness with 80% chance. So, given that the cab was actually blue, the witness will identify it as being blue with probability 80%, or in terms of fractions 0.8. Let us calculate probability B given a complement. So, what is this probability? So, this is the probability that given the cap was not blue, so the cap was green, the witness still identified it as blue. Okay? So, this is the probability that given the cap was blue, the witness made a mistake. So, he makes a mistake in identifying the color 20% of the time. So, B given a complement is 20% chance, or in terms of fractions 0.2. So, now let us calculate the various probabilities. So, probability B given A is probability A intersection B divided by probability A. This we know is 0.8. Probability A we know is 0.15. So, if you plug that in here, then you can solve for probability of A intersection B to be 0.12. Okay? So, this is one thing we have, and we have already calculated the numerator. So, now all that we need to do is to calculate the denominator, namely probability of B. So, for that again we will use conditional probabilities. So, let us first, so here we calculated probability A intersection B. Similarly, let us calculate probability A complement intersection B, just like we needed to do for the previous problem. So, B given probability of B given A complement is 0.2, and B given a probability of B given a complement we can write as the ratio of probability A complement intersection B divided by probability of A complement. Okay? And probability of A complement, it is known that it is 0.85. So, you sub that in here and you solve for probability of A complement give intersection B to be 0.17. So, now we are in good shape, because again what we will do is that we will write probability B as probability of A intersection B plus probability of A complement intersection B, and both of these two we have calculated. So, we will sub those in here and calculate the probability of B. So, this is exactly what you have. So, this is probability A given B is probability A intersection B divided by probability of B. But probability of B you write as a sum of the probabilities of A intersection B and A complement intersection B. And now you notice that all these three probabilities you have calculated already, and you sub those values in to get the chance as 41.4%. So, given that the witness has identified the offending cap as blue, the chance that it is actually blue is 41.4%. So, less than half, less than 1/2. Okay? Any questions? Okay. So, let us now move on to the concept of expectations. So, here is a motivating example for expectation. So, you are given the following two options: accept $1,000 now and flip a biased coin with a chance of 90% of getting head. If you get head, you get $1,200, whereas if you get a tail, you pay $100. So, what is the deal? So, let us examine option 2 first. So, you flip a biased coin with a very high chance of getting a head. With 90% chance you are going to get a head, and if you get a head, you are going to get a lot of money, $1,200. But if the small chance, if the event with small chance, which is the bad event of getting a tail happens, which really happens with very small chance, only 10%. If that happens, you actually have to pay. You have to pay $100. So, this is one possibility. The other possibility is that you do not go into these options and you just accept $1,000 now. So, why should you not go for the first option without thinking? Well, if you went for the second option and if the tail actually landed up heads, which it will do with a very high chance, then you will actually get more money, right? You will get $1,200 as opposed to accepting 1,000 now. So the question is that whether you will hedge your bet, how you will place your bet, right? And the other question is that if you know you will be made this offer every day for the next 365 days, which option would you pick? So let us digress to a bit to the concept of random variables. So sometimes we are interested in functions from the sample space to real numbers. So what, again, let us remind ourselves what is the sample space. So the sample space is the totality of all possible outcomes of a random experiment, and we refer to so we are interested, and you are interested in functions which depend on the outcome of the random variable. So basically depend on the outcome of the random experiment. So basically this function is obtained in the following way. So you conduct your random experiment and you get a certain outcome, and then you apply your function to that outcome. So for instance, consider the following simple function. So so your function is defined on integers between 1 and 6, and if your argument is if x is between 4 and 6, so example, so f is defined. So let's think of even f defined on real numbers. So f so consider the following function. So fx is 1 if x bigger than 3, and 0 if x is less than or equal to 3. Okay, so this function. So it just picks up 1. It picks up whether you are bigger than 3 or not. If you are bigger than 3, it returns 1. If you are smaller than 3, it returns 0. So now your random experiment is throw a fair die, and then you get an outcome and you observe f of the outcome. So what you observe is actually it's going to be random because the outcome is going to be random, but you are going to observe only 1 or 0, and you are going to observe 1 if your outcome is 4, 5 or 6. You are going to observe 0 if your outcome is 1, 2 or 3, right? So this f of the outcome is then it's a function from the set of all outcomes. It takes as argument, as input, an outcome, and it returns you some real number as answer. So these kind of functions are called random variables. And what is random about them? Well, the outcome of the random experiment is random. So when you feed it into the function, you get a random answer at the end. So what is an example? So what is another more detailed example? So when we toss a coin n times, the sample space has 2 to the power of n elements, and each of them is a string of h's and t's. Okay. So again, let us think of tossing a coin. Think of a fair coin being tossed n times, so independent tosses. And so each toss leads to a head or a tail. So let us use the symbol H for a head and the symbol T for a tail. So it's going to be a head followed by a tail, maybe followed by 2 heads, maybe followed by another tail, etc. So if you replace these heads and tails by the symbols H and T respectively, then you will get just a H followed by T followed by 2 H's followed by T, so on, right? So in general, all possible outcomes are just strings of length n, where n is the total number of tosses, and each entry of these strings are made up of H and T, right? And in principle, you could get any possible combination of H and T's as a string of size n by this coin toss. So now here is our random variable. So this is the outcome, right? The outcome is a string of length n consisting of h's and t's. What is a random variable? So for random variable, you need a function which takes as input an outcome and spits out a number. So the function we will be interested in, which we will symbolize by the symbol x, is just counting the number of heads that appear. So you take a string of length n of h's and t's and just count how many h's that are there in that string. So of course that's an integer. Any integer between 0 and n can appear. And this is an example of a random variable. And what is random about it? Well, when you do the random experiment, the string of h's and t's you get is random. So when you feed this outcome, random outcome of your experiment into the function that counts the number of h's in your string, of course you get the total number of heads which you get in your sequence of coin tosses, which is random, right? It's a random number. So this is an example of a random variable. So we will move on to more examples of random variables, but it's time to take a break of 10 minutes, and after we are back, we will continue with more examples. Okay. Okay, so let us continue with the lecture. So, before the break, we discussed started discussion on random variables, and we will continue with examples of random variables. So, two dice are tossed. So, the sample space has 36 elements. So, it's a pair of the outcomes of the two dice. So, it's a pair of two numbers between 1 and 6. So, and what you do is that you calculate the sum of these two numbers, which are the outcomes of the two dice. So, you throw two dice and you take the sum of their outcomes. So, then since both the dice are at least 1, the sum is at least going to be 1 plus 1, which is 12. Since both the dice are at most 6, therefore, their sum is going to be at most 6 plus 6, which is 12. Right. So, the sum is some number in the range 2 to 12, some integer. So, this is an example of a random variable. Okay. And why is it random? Well, the outcomes are random, so the sum of the outcomes is of course also going to be random. So, another example is a number which is picked at random from the set S, which is 1, 2, 3, 4 up to 100. And x is a random variable which gives the number of factors. So, for example, x, if you look at x, if you look at 14, then 14 is 2 times 7, and you have to, so these two are factors, and also you have to throw in 1 and 14 themselves. So, in total there are 4 factors. So, the number of factors is 14. So, you pick a number at random from the set 1 to 100. So, each of these integers between 1 to 100 have the equal chance of 1 over 100 of appearing, and then you just count the number of factors. So, of course, since the choice of the number between 1 and 100 is random, the number of factors is also going to be random, and this is going to be our random variable. So, here is another example. So, since the value of a random variable is determined by the outcome of the experiment, we may look at probabilities of the possible values of the random variables. So, for any possible value of the random variable, we can consider the event that x equal to a and consider the probability of that event. So, for example, if we were in the previous slide when we were talking about the sum of the outcomes of two dice, of course, a possible outcome is 4. So, you may ask for the probability that of the event that the sum of the outcomes of the two dice is equal to 4. Okay. So, if you think of in terms of sets, so you just list all the outcomes such that the sum is 4. So, you list all the outcomes of your experiment such that your random variable applied to those outcomes equals a. So, you take the set of those outcomes and you take the probability of that set, probability of that event. Okay. So, this is an important kind of events. We can denote it by S sub a, which is the set of all possible outcomes such that the random variable when applied to those outcomes equals a, and this is a subset of the total sample space, and therefore, it is an event. It is the event that x equal to a. So, this is just stating the event x equal to a in mathematical terms. Okay. So, here is an example. So, probability of random variables. So, 3 fair coins are tossed, so independently of each other. Let x denotes the number of heads that appear. So, what is the probability that x equal to 0? Now, let us look at the event that x equal to 0. X equal to 0 means that no heads appear, which means that the outcome of all the coins must be tails. So, it is the probability of TTT, and you can see that this probability is 1/8 in 2 ways. One way is that all the outcomes are equally likely. So, it is a string of length 3 consisting of h's and t's. So, in total there are 2 to the 3, which is 8 possible strings, and all possible outcomes, that is all possible such strings, are equally likely. So, the probability of any particular string, which is for example the probability of TTT, is 1/8. So, this is one way. The other way is that the 3 tosses are independent of each other. So, probability of t t t is probability of t times probability of t times probability of t, because because the outcomes of the 3 tosses are independent of each other, and whenever you have independent events, the probability of those events occurring together splits as the product of the probabilities. So, again probability of t for each experiment is 1/2. So, their product is 1/8. So, these are 2 ways of seeing that the probability of t t t is 1/8. Both ways are correct. So, now let us ask for the probability that x equal to 1. So, 3 tosses of the coin and one of them, and there is exactly 1 head. So, what are the outcomes which favor this eventuality? What are the outcomes which lead to the result that x equal to 1? Well, there is going to be exactly 1 h and 2 t's. So, the relevant strings are TTH, THT and HTT, and the probability of these is there are 3 possible outcomes out of 8 possible outcomes in total. So, 3/8. Similarly, probability of x equal to 2 is 2 h's and 1 t, and you can similarly calculate it to be 3/8. Probability x equal to 3 is all the 3 must be heads. So, probability of h h h, which is again 1/8. And notice that the total sum is 1, because x, which is the number of heads, will be exactly some number between 0, 1, 2 and 3, and so the probability of x being 0 plus the probability of x being 1 plus the probability of x being 2 plus the probability of x being 3. So, that is the sum of the probabilities of x being its various possible values must be equal to 1, right, because in total the total chance of all possible outcomes or all possible eventualities of x must add up to 100%. Any questions? Okay. So, let us now go to expectations. So, now that so far we have studied random variables. So, if you have a random variable, a natural thing which you can calculate about the random variable. So, one natural thing we have already calculated about the random variable is is the probability of the random variable being equal to a specific value, right. So, we already saw some examples of that. So, now what we will do is that we will calculate, we will study another concept, another quantity which you can calculate for a random variable, and that is the expectation of the random variable. In ordinary language, it is just the mean of the random variable. So, you do some random experiment, some complicated random experiment, and apply some function x on the outcome, and you get a number in the end. So, you might ask the question that what is this number on average. So, this concept exactly is the expected value or the expectation of the random variable x, and it is defined as follows. So, it is a weighted sum of all the possible values of x. It's a weighted, the expectation of x is the expected value of x is a weighted sum of all the possible values of the random variable capital X, weighted by the probabilities that capital X takes that particular value. So, this is exactly a weighted average of the possible values of x, each value being weighted by the probability that the random variable capital X assumes that value. Okay. So, you can also denote the values by AI, and then this is just summation over AI, probability x equal to AI. Okay. So, let us take an example. So, a vendor sells 50 bottles of drinks on a hot day, 30 bottles on a normal day, and 15 bottles on a cold day. So, of course, if the day is hot, the sale of drinks is more. Whereas if the day is cold, the sale of drinks is less. So, he buys each bottle of drink for 20 cents and he sells it for 80 cents. The probability that a day is hot, normal or cold is 0.3, 0.5, 0.2. Find the expected daily profit from the sale of the drinks. Okay. So, what we will do is that we will form an equation in terms of the profit in terms of the various quantities, and then we will then we will calculate the expectation. So let X denote the daily profit. So what are the possible values? On a hot day, he buys a bottle. So he always buys a bottle with he always buys a bottle with 20 cents and sells it for 80 cents. So he gets 80 cents and he spends 20 cents to buy the bottle. So the balance is his profit per bottle, which is always 80 minus 20 cents. Okay, this is profit per bottle. Now, on a hot day, he sells 50 bottles. So total profit is 50 times profit per bottle, which is $30. On a normal day, he sells 30 bottles. So the total profit is 30 times profit per bottle, which is $18. On a cold day, he sells 15 bottles. So the total profit on a cold day is 15 times 15 times profit per bottle, which is $9. So now we have so these are the possible values of the random variable, which is the profit. So by the way, why is the profit random? The profit is random because the value of the profit will depend on whether the day is hot, normal or cold, which is a random event having certain probabilities. So the probability of so now we have investigated the random variable X, and we have calculated its possible values, which is $30 on a hot day, $18 on a normal day, $9 on a cold day. Probability of a hot day is 0.03, normal day is 0.05, cold day is 0.2. Sorry, probability of a hot day is 0.3, normal day is 0.5, cold day is 0.2. So the expected profit is just the weighted sum of the value of X weighted by the probability that it takes that particular value. So if you form the weighted sum and weight it against the probability of having a hot day, a normal day or a cold day, you will get the expected profit as $19.80. Okay? Any questions? Okay. So let us continue with expectations. So two fair dice are thrown. Find the expected value of the total score obtained. So again, you think of the total score. So the total score, as we noted, if you throw two dice at random, so fair dice, and the results of the two dice are independent. So it's a pair of numbers, each number between 1 and 6. So there are 36 possibilities in total, and each of these 36 possibilities is equally likely. Now what is the sum, since each of the outcomes of the two dice, each of the numbers on the two dice is at least 1. We have already noted that the sum of these observations is going to be at least 2. And since the outcome of each die is at most 6, therefore the sum of the observations is at most 12. So the sum of the two observations of the dice is a number, some integer between 2 and 12. So here is a list of the various integers between 2 and 12, and let us calculate the probabilities in terms of probabilities of X assuming these values between 2 and 12. So X is the sum. So now the point is that how do you calculate the probability of X being equal to 4, for example? Well, X can be equal to 4, so you just count. So each outcome is equally likely. Each pair of outcomes, each pair of numbers on the two dice is equally likely, and this probability is equal to 1 over 36. So basically the probability that X equal to 4, for example, is going to be the number of outcomes which sum to 4 divided by total number of outcomes. So total number of outcomes is 36. What is the number of outcomes which sum to 4? Well, the sum, if two of these numbers sum to 4, then it can happen in 3 ways. So first of all, both of the numbers could be 2. That is okay, the sum is 4. Or first one could be 1, the second one could be 3. The other option is that the reverse, so the first one could be 3, the second one could be 1. And these are all the possibilities, because it cannot, none of the numbers can go below 1, right? So the total number of outcomes which sum to 4 is 3. So the probability of x taking that value is 3 over 36. So it's that simple. So similarly, you calculate all the other probabilities, and the expectation of x is the sum over the possible values of x weighted by the probability of the sum taking that value, and using this table you can calculate the expected value to be 7. Okay? Any questions? Okay. So let us now go to another example of expectation. So a coin is tossed 5 times. The probability of head is p, and the tosses are independent of one another. Find the expected number of heads obtained. So x, let x be the number of heads obtained in 5 tosses. So probability of head in each toss is p, is small p. So probability of tail is q, which is 1 minus p. So now what is the probability of the sum being, what is the probability? So x is the number of heads obtained in 5 tosses. So what is the probability? So let us calculate the probability. So what is the probability that x equal to 0? So which means that 0 heads are obtained. So all the outcomes are tails. So probability of getting a tail in any toss, so it is probability t, 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 this string. Probability, now the tosses are independent, so it is probability t times probability t times probability t, 5 times, because there are 5 t's in the string. Now the probability of getting a tail in any particular toss is q, which is 1 minus p, so this is q to the 5. Okay. Similarly, what is the probability of getting one head? Well, it's going to be a string of h's and t's, length 5, exactly 1 h. So how many such strings are there? You just need to find where you are going to put the h, and the rest will all be t's. So the number of ways you can put one h in 5 slots is 5 choose 1, which is 5. And then you multiply that by the probability of every outcome consisting of 4 t's and 1 h. Again, you use the fact that the tosses are independent, so it splits into a product of probability h and probability t's. There are 4 t's, and probability t is q, so q to the power of 4, and only 1 h, and the probability of h is p, so times p. Okay. So similarly, you can see that the number of outcomes in which there are exactly 2 heads is 10 q cubed p square, because for any such string, the probability of the outcome being that string is q cubed times p square, and the total number of strings with 2 h's and 3 t's is equal to the number of ways of choosing the spots for the 2 h's out of 5 possible slots, which is 5 choose 2, which is 10. Okay. Similarly, you can calculate the other probabilities. Okay. So now, expectation of x is summation over x, little x probability capital X being equal to little x, and now you substitute the values from this table, and you get this, and you can simplify it, and here you use the binomial expansion of the binomial theorem for p plus q whole to the power of 4, to write this as p plus q whole to the power of 4, but q is 1 minus p, so p plus q is 1, so this is 1, so this is just 5p. Okay. Any questions? Okay. So you might imagine that these kind of calculations are very complicated and cumbersome, but actually it is not so. because what we can do is that we can take recourse to a fantastic property of expectation, which is called linearity of expectation. So, this is often very powerful in solving problems. So, suppose you have a bunch of random variables x1, x2, xk, and x, the random variable, is their sum. Okay. So, what is a simple example? Suppose you are throwing 2 dice and your ultimate random variable is the sum of the 2 observations. So, now you can define 2 random, so let us call that x. So, x is the sum of the 2 observations on the 2 dice. Now, you can define 2 more random variables x1 and x2, where x1 is the outcome of the first die, which is a number between 1 and 6, and x2 is the outcome of the second die, which is another number between 1 and 6. So, x, which is the sum total of the outcomes of the 2 dice, is the sum of x1 and x2, which are the outcomes of the 2 individual dice. Okay. So, this is, so it's a natural it's a natural scenario to consider, where one random variable of interest is actually a sum of many other random variables. Okay. So, then we have expectation of x is expectation x1 plus expectation x2 da 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 up to expectation xk. So, say if there is a linear relation between x and the xi, namely x equal to x1 plus x2 da 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 up to xk, then the same linear relation holds between expectation x and the expectation xi, namely expectation x equal to expectation x1 plus expectation x2 plus da 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 up to expectation xk. Okay. And here is a simple argument to see why this is the case. So, expectation of x is the probability of, is the sum over all outcomes is a sum over all outcomes, probability of that outcome times x applied to that outcome. Because if you take an outcome and use it as an input, apply x to the outcome as an input, treat the outcome of the random experiment. So, the outcome of the random experiment is s, and you feed that outcome of the random experiment into the random variable x as an input, then you get the value of the random variable, right. So, this is the value. So, again what did we see before? We saw that the expectation of a random variable is a weighted sum of the values. So, x applied to the x applied to the outcome of the random experiment is the value of the random variable, and this is the probability of the outcome, and P of s is the probability of that particular outcome of the random experiment materializing. So, this is the weight. So, again it is a weighted sum of the values of the random variable. So, it is the expectation, and now you are in good shape, because you can write x as the sum of the xi's. So, x of s is just the sum of the xi's of s, and this is going to be xk, typo, and now you just it's simple algebra. Now you just slot the P of s inside this summation. So, this is the summation of P of s times the xi of s, and then you just separate these sums to get summation I is equal to 1 to k summation over s P of s xi of s. Okay. So, you just separate these sums, you split this bracket into sums depending on the index 1, 2 up to k, and then you notice that each of these sums within the bracket is expectation of xi. Okay. So, this is indeed the sum of the expectations of the xi's, just to get a picture of why this should be true intuitively. Okay. So, now any questions? So, let us take an example of expectation. So, motorist has a choice of two routes to drive from A to D. There are three stretches of roads A, B, B, C and C, D, for which the duration of travel in minutes is denoted by the random variables x1, x2 and x3. So, for each stretch, the duration of travel can take three possible values with certain probabilities which are given, and so the possibility is the following. So, route 1 consists of three stretches, and for each the length of time taken to traverse each stretch A, B, B, C or C, D is random because of traffic issues, let us say, and the distribution is known. So, this random time taken to traverse the distance between any of these 2 points A and B or B and C or C and D is random, and they are can take certain values 5, 6 or 7 with certain probabilities which are known. So, this is one way to go. The other way is to take a highway bypassing B and C. So, you just take a highway, but of course, it is directly a highway between A and D, and of course, it is going to be longer than the individual stretches, but in totality it can be 18 or 23 with certain probabilities 0.9 and 0.1. So, the question is that whether he should take the highway or whether he should go through the little roads in the three stretches. So, to answer this question, what we will do is that, whatever the driver does, the time taken in each of these two routes is going to be random. So, of course, it will always happen with certain probability one of the routes will be better than the other. So, that way he cannot compare. In order to compare, he needs some score for the two routes, and the route which has the better score will be his chosen route, right. So, this better score is actually, so this score for a route is going to be the amount of time which he expects to take if he takes that route. Okay. In other words, the total time taken by the motorist to go from A to D using these two routes are going to be random. What he will do is that he will calculate the expected values of these random times taken in the two routes and compare these two expected values, and whichever gives him the favorable expected value for the time, which means the lower expected value for the time taken to traverse between A and D, will be his chosen route. Okay. So, here is a solution. So, all that we need to do now is to calculate the expected time taken in route 1 and the expected time taken in route 2. So, what is the time taken in route 1? The time taken in route 1 is the time taken between A and B, the time plus the time taken between B and C, plus the time taken between C and D. So, now we take, so x is naturally the sum of these three times for these three stretches. So, x is naturally x1 plus x2 plus x3. So, expectation x is expectation x1 plus expectation x2 plus expectation x3. So, now all that you need to do is to calculate these expectations, and for these expectations the distributions are given here, the values that the exercise takes and the probabilities of the exercise taking those values, and you just substitute these values in the definition of the expectation of x k and get the expectation of x k to be 6. So, the expectation of x, which is the sum of the expectation of the xi between 1 and 3, is 18. Okay? Clear? Any questions? So, now this is the time taken, expected time taken for the route 1. For route 2, he just takes a stretch of highway between A and D. So, he wants to, if the time taken is y, he wants to calculate the expected value of y. So, again it is the values of y weighted by the probability of taking those values. So, you take the weighted sum and you calculate it to be 18.5. So, it turns out that the time taken, the expected time taken in the highway is longer than the expected time taken in the going through the little stretches of road. So, of course, he will prefer the little stretches of the road. Notice that with probability 0.9, so with probability 90%, his time in the highway is going to be equal to the expected time in route 1. But with a small chance, he might get stuck in a bad traffic jam on the highway with a small chance. So that really makes his expected or average time taken in the highway to be much larger. So that's kind of the moral of the story. Okay? Any questions? So if there are no further questions, let us stop today here, and in the next week, in the next lecture, we will begin with indicator random variables and their applications. Okay?